How can a plane born in the 1950s continue to dominate the skies in 2050? It's not a Miraculite strategy. The B-52 Stratofortress, a symbol of the US Air Force, has outlived all expectations thanks to its flexible design, upgrade-ready structure, and now the largest overhaul in its history with the Rolls-Royce F-130 engine. From the Cold War to hypersonic missile tests, from AESA radar to full digitalization, this 70-year-old flying fortress is living proof that modernization doesn't have to start from scratch. And perhaps the most surprising part, technologies born for war may be paving the way for the future of civilian aviation. The B-52 Stratofortress, a strategic aircraft of the US Air Force, has now passed the 70-year mark, with the first unit delivered on June 29, 1955, and 72 aircraft still in service as of 2025. In the modern aviation era, where most contemporaries have long been retired, the B-52 remains standing strong, a symbol of durability and adaptability. Part of its extraordinary longevity lies in its original design. The B-52 was built tough yet simple, with ample room for upgrades in radar, avionics, communications and weapons systems, all without having to redesign the entire airframe. That flexibility allowed this aircraft to evolve with the times, from the Cold War to modern campaigns such as battlefield support and hypersonic missile testing. Currently, the Commercial Engine Replacement Program (CERP) is underway to upgrade the entire B-52 fleet with Rolls-Royce F-130 engines. The project involves the production of over 600 engines at a cost of approximately $2.6 billion, aimed at extending the operational life of the B-52 well into the 2050s, possibly even to its 100th birthday, as the B-52J, making this the most significant upgrade in the aircraft's history. Compared to the aging TF-33 engines from the 1960s, the F-130 promises 30 to 40% better fuel efficiency, lower maintenance costs, and greater long-term reliability, while preserving the original design flexibility that the B-52 was built with. Combined with upgrades such as AESA radar, digital avionics, modern communication systems, and long-range weapons, the B-52 is being reborn not just as an old aircraft, but as a 21st century strategic icon, a legacy platform that continues to evolve. Although developed for military purposes, the F-130 engine is a remarkable product of Rolls-Royce technology, based on the BR-725 commercial platform that has proven its efficiency and reliability on business jets, like the Gulfstream G650, G700. What makes the F-130 unique is its 30 to 40% fuel efficiency improvement, reduced need for overhauls, and integration of a modern FADEC control system and line-replaceable units, all of which reduce aircraft downtime and operational costs. The US Air Force could no longer afford to delay replacing the TF-33, an engine only intended for use in the 1960s, now well beyond its design life and extremely costly to maintain. Choosing the F-130 was a strategic decision. It requires no major structural changes, reduces integration risks, and saves both time and development cost. Moreover, the B-52 was originally over-engineered in the 1950s, meaning it was built with structural flexibility, capable of handling AESA radar upgrades, digital communications, and long-range weapons without needing a complete airframe redesign. Thanks to these advantages, even after more than 70 years, the B-52 remains adaptable to modern technologies, ready to play a key role in global strategic aviation, not only in military operations, but increasingly in civil applications of the future. While the B-52 Stratofortress still appears formidable on the outside, its internal systems are being pushed far beyond their intended lifespan. At the heart of this strain are its TF-33 engines, originally installed in the early 1960s and no longer produced since 1985. Though the aircraft remains structurally sound, these engines have drifted far from modern safety and performance standards. The consequences are mounting. Replacement parts for the TF-33 are increasingly scarce, forcing technicians to scavenge from long-retired units in storage depots or fabricate components by hand. Maintenance costs are skyrocketing, servicing. A single TF-33 can cost up to $2 million every 6,000 flight hours. Worse, the engines rely on small suppliers and outdated procedures that make logistics slower, more fragile, and more expensive with each passing year. More critically, the B-52 lacks an integrated starter system and must use a cartridge starter, small explosive charge that slashes engine startup time from over 60 minutes to under 10. However, this legacy method is not only noisy and environmentally harsh, but also ill-suited for many modern operational environments. Fuel consumption is another significant burden. The TF-33 burns over 3,000 gallons of fuel per hour, about 50 gallons per minute. With the B-52 fleet flying roughly 38,000 hours annually, total fuel usage exceeds 117 million gallons each year, translating to over $272 million in fuel costs alone. When combined with maintenance, labor, and the struggle to source rare parts, the total cost becomes staggering. According to recent data, the B-52 now costs around $70,000 per flight hour to operate, making it one of the most expensive aircraft in the US Air Force. A pivotal report in 2017 declared that the TF-33 would become unsustainable shortly after 2030, and with no new parts available for decades, its future became untenable. The Government Accountability Office (GAO) further emphasized that the engine would no longer comply with safety or performance standards beyond that point. In addition to these long-standing challenges, the development of the F-130 replacement engine encountered an early obstacle. Engineers identified airflow distortion within the air inlet system, which required a complete redesign. This issue has delayed the critical design review to 2026 and pushed back the broader program timeline. These compounding factors left the US Air Force with a clear choice. Piecemeal upgrades were no longer viable. Instead, the entire fleet of TF-33 engines would be replaced with F-130s under the Commercial Engine Replacement Program, CERP. This is not merely an upgrade, it is a strategic leap forward, essential to maintaining flight safety, reducing operating costs, and preparing the B-52 for a future shaped by advanced aerospace technologies. Since the mid-2000s, maintaining outdated TF-33 engines was clearly no longer a viable option, maintenance was increasingly costly, parts were scarce, and technical risks were growing. The US Air Force decided to replace the entire engine fleet with the F-130, chosen as the solution under the CERP program, valued at over $2.6 billion, aiming to re-engine all 76 B-52H aircraft and lay the foundation for the new B-52J variant under contract. The F-130, based on the commercial BR-725 platform, retains a comparable thrust output to the TF-33 at approximately 17,000 pounds of force. It delivers 30 to 40% better fuel efficiency, increases range and payload capacity, and remains compatible with the aircraft's original design, avoiding complex structural redesign of the airframe. From a maintenance perspective, the F-130 is a breakthrough. It requires no engine removal for overhaul throughout its operational life on the B-52J. Its design follows the line replaceable units principle, allowing technicians to quickly swap parts on the aircraft, its increasing readiness and minimizing downtime. According to the plan, Rolls-Royce will complete the CDR by the end of 2024, moving into flight testing in 2025, including air inlet testing at NASA Stennis, aimed at reducing risk before installing the engine on actual aircraft. Digital engineering plays a major role in accelerating design and testing, reducing delays in a program expected to stretch into 2035-2036. More than a military hardware project, the F-130 also boosts domestic technology. Over 650 engines will be built in Indianapolis, creating more than 150 new jobs and supporting various US high-tech companies. Innovations such as FDEC, advanced thermal management, and composite materials have potential civil aviation applications, paving the way for a new generation of fuel-efficient, sustainable engines. The F-130, derived from the proven BR-725 commercial engine, promises 30 to 40% better fuel efficiency compared to the TF-33, a major logistical upgrade. As one Reddit user noted, the F-130 should deliver about 30% better fuel efficiency and far fewer maintenance hours, despite providing similar thrust about 17,000 bell of fare. The F-130 does not require changes to the aircraft's wing structure for installation, preserving climb performance and tactical payload capacity without increasing design costs. One of the F-130's biggest advantages is longevity. Its design eliminates the need for a full engine overhaul throughout its service on the B-52J, significantly reducing aircraft downtime and maintenance costs. Under current plans, the F-130 can operate reliably through 2050 without engine teardown. Overall, the F-130 not only improves thrust and range, it also fundamentally reshapes the operational cost structure of the entire B-52 fleet, from fuel to long-term maintenance. This enhances both reliability and combat effectiveness. In short, the F-130 isn't just a strategic leap for the B-52J. It has the potential to become a core technology for the next generation of civilian jet engines, especially in the drive for fuel efficiency, lower emissions, and sustainable operations. The F-130's thrust supports more than just takeoff, and climb. It improves payload capacity and performance at altitude, especially in hot climates and thin air conditions. The first test took place at NASA's Stennis Space Center, where Rolls-Royce successfully ran the first twin-pod configuration, simulating the B-52's actual engine setup. These tests validated crosswind performance and stable FADEC operation, reducing future integration risks. After clearing CDR in late 2024, the F-130 will enter high-altitude testing at the Arnold Engineering Development Complex in Tennessee. This phase is scheduled to begin in February 2025. The state-of-the-art test facility can simulate flight conditions at altitudes up to 75,000 feet and speeds of Mach 1.2. It will be used to evaluate the engine's heat resistance, performance in low air density, and ability to withstand high-pressure environments under military strength standards. In parallel with field testing, Rolls-Royce uses low-speed test rigs at its Indianapolis Test Cell 114 to collect early software data and confirm engine stability on the ground. Notably, the Army ERDC team has adopted digital engineering tools. These include aerodynamic simulation software and the HPC MP Create platform. As a result, real-world testing time has been reduced by up to a full year compared to traditional programs. These crucial tests not only ensure that the F-130 performs in all flight conditions, they lay the groundwork for delivering the B-52J with full operational capability in the coming years. Rolls-Royce has implemented several major technical innovations in the F-130, from high heat-resistant composite materials to one-piece titanium blisk fan blades that reduce wear, to a fully autonomous FADEC control system that optimizes thrust, fuel use, and predictive diagnostics. These features are now standard in modern commercial aviation. Notably, Rolls-Royce also applied fully integrated digital modeling, simulating the entire engine mount wing system, minimizing the need for structural changes when installing the F-130 into the old B-52 airframe. This represents a breakthrough in applying military engineering to civil aviation design, reducing risk and increasing operational and maintenance efficiency. These technologies don't just elevate the B-52J's strategic platform, they serve as the catalyst for the next generation of civil aviation propulsion, fuel-efficient, long-lasting, and both powerful and sustainable. The F-130 is not merely a new engine for an old airframe. It is proof that sometimes radical transformation doesn't require starting from scratch, it only requires knowing where to upgrade, what to preserve, and how to apply the best of today's innovation. From tests in the Nevada desert to tomorrow's commercial flight paths, Technologies once born for war are now quietly reshaping civil aviation lighter, quieter, more precise, and more sustainable. The F-130 isn't just giving the B-52 a second life, it's rewriting how the entire aviation industry thinks about modernization. Because sometimes, the furthest leap forward begins from the strongest place we already stand.